In this tutorial, we will be discussing solution stoichiometry. In solution stoichiometry, we determine the amount of the product with the solution concentration. So we're using the information that we learned about molarity and relating it to the chemical equation. We still need to convert it to moles, because remember, those coefficients in front, the numbers in front of the compounds on chemical reactions, always relate to moles. Moles are the end caps to our plan. And we still need those coefficients. So suppose that we want to know the mass of CaCO3 that's required to react 25 milliliters of 0.75 molar. Notice I keep everything under the appropriate compound. It helps me keep myself organized. Also notice that it's giving us information about one and asking about another compound. That means we're going from one compound to another, which means that we're going to have that horizontal arrow, which means we have moles as the end caps and coefficients as the conversion factor. We need to go from molarity to moles, and then over here we need to go from moles to grams. Instead of using an actual conversion factor with this process, I'm going to use the equation. You can, however, make it a conversion factor if you'd like. However, I'm going to just simply use it as an equation and transfer it that way. And then to get from moles to grams, grams is our key term for molar mass, which means that we need to look at the periodic table. I'm assuming at this point you know how to do that. And so the molar mass of calcium carbonate is 100.09 grams is equal to 1 mole. Alright, so let's do this part first. Let's do the molarity first. Molarity is equal to moles over liters. We have 0.75 molar is equal to X over, this is 25 milliliters. We need to convert the milliliters to liters before we can go on. We do that by dividing by 1,000. There's 1,000 milliliters in 1 liter. Because of this being in liters, I have to convert that first. 0.025 liters goes on the bottom. Cross multiply to find the X. That comes out to be 0.01875 moles of HCl that's been used. That is now going to be our first number in our bracket. Moles HCl over 1. In our plan, we are right here now. We need to get from moles of one to moles of the other. To do that, we use the coefficients. We have moles of HCl on the top. That means I'm going to put moles of HCl on the bottom. And that's 2. We need 1 mole of CaCO3 because there's a 1 in front of there that's invisible. We are now here on our plan, and we need to get up to grams. So for every 1 mole of CaCO3, there are 100.09 grams. And that comes out to be 0.01875 divided by 2 times 100.09 is 0.938 grams CaCO3. We can also use the same process with limiting reagents. So if in the reaction shown above, we have 123 milliliters of a 1.00 molar NaCl is mixed with 72.5 milliliters of 2.71 molar, how many grams of AgCl can be produced? So we have information about both reagents. Whenever you have information about both reagents, that means you need to find the limiting reagent before you determine the theoretical yield. So we just do it one at a time. We need to get from molarity to moles, and we use the equation. Then we get from moles of NaCl to moles of AgCl. We do that with the coefficients. And then moles of AgCl up to grams using the molar mass. The molar mass of AgCl, by looking at the periodic table, is 143.32 grams per mole. And we're going to do the same thing over here. We need to get from molarity to moles, and then moles of AgNO3 to moles of AgCl up to grams. So we're going to actually have two problems in the same question. So 1.00 molar is equal to X over, this is a milliliter, so I have to convert that to liters by dividing by 1,000. And that comes out to be 0.123 liters. So we are starting with 0.123 moles of NaCl. So we can go ahead and do this now. This number now goes over 1. We have moles of we are right here in our track. We have moles of NaCl on the top. That means I need 1 mole of NaCl because the coefficient of NaCl is 1. We go to the coefficients to bring us over here. Coefficient of AgCl is 1. And we're trying to get to grams. For every 1 mole of AgCl, there's 143.32 grams. So 0.123 times 1 divided by 1 times 143.32 comes out to be 17.6 grams AgCl. Alright, that's one possible answer. Let's do this silver nitrate next. First thing we need to do is figure out the molarity. So I'm going to do that over here since I'm running out of space. 2.71 molar is equal to X over, I need to figure out what 72.5 is in liters. (1,000 milliliters), 1 liter. That comes out to be 0.0725. That means X is equal to 0.196 moles AgNO3. That's going to be our starting number for our lines. 0.196 moles AgNO3 over 1. We have moles of AgNO3 on top. That means we need to put moles AgNO3 on the bottom. 1 is the coefficient for that. We're converting it over to AgCl. So 1 mole AgCl. And then for every 1 mole of AgCl, because now we're here, we need to get to grams, is 143.32 grams. So 0.196 times 1 divided by 1 times 143.32 comes out to be 28.09 grams. You pick the smaller of the two numbers because the other one will be in abundance. So NaCl is the limiting reagent, and that brings us to 17.6 grams of AgCl. We're going to have one more example. Calculate the number of milliliters. So we're looking for milliliters this time of a 2.00 molar HNO3 solution required to react with 216 grams of Ag according to the equation. So we're given information about one compound, we're being asked about another. So we have a horizontal line. Moles are the end caps. That means we need coefficients because it's a horizontal line. We're going from grams to moles, which means we're going to need the molar mass. Looking on the periodic table, we find that silver is 107.87. And then to get from moles to milliliters over here, we're going to use the molarity equation. Alright, so 216 grams of Ag over 1. We have grams of Ag on the top. We need to put grams of Ag on the bottom. That's 107.87. And that's 1 mole of Ag. We have moles of Ag on the top, so we put moles of Ag on the bottom. We are right here right now, and we're trying to get over here. So that means we need the coefficients. 3 moles of Ag, 4 moles of HNO3. This time, it's not asking about grams, it's asking about milliliters. So we don't need the molar mass of HNO3. So we're going to stop there. And that gives us 2.67 moles of HNO3. So how many milliliters do we need? Well, we have a 2.00 molar solution. We need 2.67 moles. We need to figure out the liters. I'm going to go ahead and cross multiply first. So 2.00 times x is equal to 2.67. Now I'm going to divide, that's moles, both sides by 2.00 molar. This one cancels out, so that means x is equal to 2.67 divided by 2.00, 1.33 liters. It's asking about milliliters. So make sure you're answering the question that's asked. 1.33 liters over 1. In every 1 liter, there's 1,000 milliliters. So that comes out to be 1,330 milliliters. This here is where most people are messed up on the molarity. The 2.67 gets into your calculator first. So make sure that you remember to cross multiply before you divide. The most common mistake is people will put 2.00 divided by 2.67 when it's supposed to be the other way around. Right. And that is how to do stoichiometry with solution concentrations.